I am Nazam.
I am a computer science student and I'm learning quantum mechanics for fun. I have some background in physics, but I've probably forgotten parts of it. And I'm taking a quantum mechanics class in college right now, and I want to practice and do some active learning by actually explaining what I learned so that I understand the material better. I'll be doing all of this inside Obsidian, which is a note-taking software. I created a new vault called Quantum, and the structure of the vault is the following. We have the main page where I keep all the topics organized. Then we have a folder for concepts, for the key ideas that I encounter. Then derivation and details. These are short notes with numbered titles so they don't take up too much space. They are for steps and derivations that I might forget later. Then we have a folder for experiments, especially important since quantum mechanics is full of thought experiments. The first chapter of the book I'll be following is based on experiments. Then formulas for specific equations, also stored with numbers. Graphs, these are pictures that I'll draw on my iPad and paste into notes. Topics, bigger sections starting with the Stern-Gerlach experiment. Questions is a note for questions that I might ask my professor. And there is also a note for refreshing my knowledge. Some topics are concepts I already learned before, but I want to revisit later. I'm also using the Zettelkasten method of note-taking, though maybe not perfectly. Basically, each note should cover only one concept. That way, everything stays clean and organized. Let's begin with Stern-Gerlach experiments. The first chapter of the book I'm following, A Modern Approach to Quantum Mechanics by Townsend, is about these experiments, and it starts with the original Stern-Gerlach experiment. It showed that intrinsic spin angular momentum can take only two values, positive and negative h bar over 2, which we call spin up and spin down. Here's how it worked. A collimated beam of silver atoms was sent between two magnets, one flat and the other with a sharp tip, which created an inhomogeneous magnetic field. The goal was to study the relationship between the electron spin and angular momentum. What they found was that instead of spreading out continuously, the atoms split into only two spots. This showed that angular momentum isn't continuous, it has discrete values. Now, here's something I didn't fully understand at first. So, why is there a sharp tip on one of the magnets? See, I forgot some things. That's why I made a separate note explaining this in detail. Basically, the sharp tip makes the magnetic field stronger near the bottom magnet. As we go up along the x-axis, the derivative of the magnetic field with respect to z is negative because the field decreases. Because the electrons have a negative magnetic moment, spin up corresponds to a positive force along z. And I have formula for the force right here. So spin up electrons deflect upward, while spin down electrons deflect downward. The force equation shows that multiplying two negatives gives a positive, which explains the upward deflection for spin-up electrons. Finally, I kept linked concept pages like magnetic moment and intrinsic spin angular momentum, so I can jump to them whenever I need a refresher. That's the original Stern-Gerlach experiment. Let's move on to the first thought experiment. We start with two Stern-Gerlach devices, SG devices, oriented along the z-axis, so SGZ. We send a beam of atoms into the first device. Two beams come out, spin up and spin down. We block the spin down beam so that only spin up atoms continue here. Now, when those spin up atoms go into a second SGZ device, they all come out spin up again with 100% probability. This shows an important principle that if you measure the same observable twice or more than twice, you get the same result. The outcome doesn't change. The second experiment is, instead of sending the atoms into another SGZ device, we send them into an SGX device, which measures spin along the x-axis. Here things change. The spin-up atoms from SGZ device come out of SGX as a 50-50 mix. Some spin up and some spin down along the x-axis. This is because measuring spin along z makes the spin along x indeterminate. In other words, once you choose to measure a different axis, the previous information no longer holds. We erase that information. Third experiment. This is a longer one. We put an SGX device in between two SGZ devices. We start with spin-up atoms from the first SGZ device. We filter again, taking only spin-up from SGX and send them into a second SGZ device. We might expect them to all still be spin-up because the ones that entered SGX device right here are all spin-up. But no, they come out indeterminate again. Kind of, it seems like spin-down atoms appear out of nowhere, but what's happening is that the measurement along x-axis changed the state. It erased the earlier information about z. This illustrates that spin along z and spin along x cannot be both known with certainty at the same time. Another way to say it is that the particle leaving SGX is in a superposition of states along the z-axis. We can describe this with ket vectors. These are the ket vectors, and the state is a linear combination of plus c and minus c with coefficients that represent probability amplitudes. Their squared magnitudes always add up to 1. They follow normalization. This is one of the fundamental rules of quantum mechanics. Here, inside another page, I explain how they add up to 1. Fourth experiment. Now we introduce a modified SGX device, one that recombines the beam so that the output is the same as the input if we don't measure them. This is the key part. When we don't measure, we see that all of the atoms that enter the modified SGX device are spin up, and when they enter SGZ device, they are still spin up with 100% probability. Finally, for the fifth experiment, instead of the second SGZ device, we put an SGY, measuring the spin along the y-axis. The result is similar to experiment 3. Again, the outcomes are split, but here we learn that complex numbers are essential for describing quantum mechanics. In classical physics, you don't really need complex numbers, but at the quantum level, the math requires them. For example, in the transformations between different spin directions. This is where we use the bracket notation. We can calculate the probability of one state turning into another by taking the inner product. These probabilities almost always involve complex numbers. That's the overview of the 5 thought experiments. Each one builds on the previous, and here's the summary. See you next week.